this suit, basically when firefighters go in the field, they want to do two things. First, they want to communicate to their team, and to do this right now, they use a radio that they trigger manually, which can be a problem if there are interaction. So, they want to communicate efficiently to the others, and also the suit that we want to build will have some capabilities, like telling them the temperature outside, different kind of stuff that also they want to be able to trigger. So, given all this stuff we want to build and integrate into the suit, this challenge is focused on the voice processing part. So, the set of commands that we want to build in the suit needs to be triggered vocally, so by specific keywords. That's the first problem. And then the communication to the others needs to be detected and broadcasted by streaming. So all the suits will be connected on the field, and basically the firefighters, when he's in a mission, he will talk to his teammates, who will broadcast this, and he will also trigger commands using a keyword. So that leads to this challenge. Basically, we're trying to reproduce this voice processing part, where here, I'll talk about this. You have an audio sample that I recorded that contains communications, so random communications, and that contains a voice command. And a voice command is basically defined by a keyword. The keyword is galactic, plus one word that identifies the command. So if the firefighter needs to know the temperature of its suit, it will say galactic temperature, and that's the command. So we need to detect that. So here in red you have two commands, and in green these are communications that needs to be broadcasted. So again, on the requirements, basically we want the communication to be broadcasted, but we don't want the command to be broadcasted because it pollutes the whole team efficiency. If they are all in the field and the commands are broadcasted, we don't want that. So we will start from this audio file, and to mimic the real-time constraints, this so as I said, it will be broadcasted. The voice will be broadcasted. So it will be streamed frame by frame. So if you take this audio file, it has samples, so from a microphone recorded. And how streaming works is that each samples are assembled into packets. That's called a frame. So a frame is 512 samples, and these samples are sent at a certain rate. So that's how it works in real. So the challenge is it takes this file and it will reproduce the sending of the frames. And your task is basically to receive the frames. So you will receive each frame sequentially, and you need to identify each frame, whether it's a communication or whether it's a command. So, yes. Yes, please ask any question.
I'm not going to be attempting the backburner question. How do you solve the problem of tomato?
Sorry?
Tomato and tomato. How do you solve that problem? It's a voice command, right?
Sorry, I didn't get the question.
Accent and pronunciation.
Yes.
Phonetics are different.
Yes, so that's a challenge.
Tomato, you say tomato, and then the poor guy doesn't know what the hell is going on.
So,
what's the question?
How do you solve accent and pronunciation?
So that would be a challenge that we will face in real life. That will not be a challenge for this hackathon because you will only work on this file, which is my voice. I hope my
he's telling a secret.
Yeah, that's fine. Then also the scope is reduced, so we'll provide all the information, and I will describe that after. But basically, a command is defined by a keyword, which is galactic, and a word that follows it. And so in this file, for example, you have the first one, which is galactic temperature, and the other one which is galactic battery. So you can, when your focus will be on this file, and this is the scope. So yes, basically I will talk now on the setup, how you will answer this hackathon, which will also, I think, answer some questions. So basically we set up a GitHub page where you have a Python script, so your solution needs to be in Python. And this Python script, it simulates the streaming of this file. So you have one thread that just sends frames, and you have another thread when you run this Python file that receives the frames. And so your work is to work on the receiver thread. So you will get some frames, and you need to label them, whether you decide to broadcast it, or whether you decide to not broadcast it, because it's a command. Is this more clear? Yes. So then how we evaluate this, so you will put your solution in the Python file, and in the end it should run, so all the frames will be sent, you need to label them in like as fast as possible, and we will measure basically your accuracy. So each frame that is a command, so between the red lines, that you label as communication, that you said, we broadcast, that would be penalties. And each frame that are your communication that you didn't broadcast, depending on your solution, so that you missed, this would be penalties as well. So that's two ways of measuring. And the third way is obviously latency. So as I said, we will send frame by frame. So you need to label the frame as fast as possible. Because if you take the real-time problem between two firefighters, you need to basically, depending on the logic of the solution, but if you choose to detect if it's a communication and then broadcast it, you need to detect this as soon as possible, so that you don't you try to provide a communication in real time. Is this? Do you have any question on this? Yes.
Are you restricting machine? Are you restricting the machine we need to use? So can I run it say on my GPU or?
So
are there any limitations?
Yes. We don't want to put limitation on this. The only, your solution should be reproducible. And so in terms of computational power, it should be reproducible on a computer, like say a MacBook Pro kind of computational power. And
reiterate. So if you are using GPUs, the latency will be lower, correct? At inference.
Yes.
So I think the question is about inference, correct?
Yeah, we'll be publishing the specifications and capabilities of the test machine, where all of the submissions will be tested on the same machine. So you'll know what that is, which you'll be able to recreate in an Amazon instance. So you'll be able to have exactly the same compute as we'll have when we're comparing all the side-by-side submissions.
Yes, so on the computational power, yes, that will be fixed for everyone, sorry. And in terms of your solution, as I said, there is a Git on which basically you will create your branch. There is this main Python script in which your solution will needs to fit in the end. You need to code this receiving thread to label, but then you're free to structure your solution in as many files as you want. The only constraint is that it should be reproducible. So we will evaluate each solution, we'll clone your branch on the machine, and we will run it, and it should work, and we will evaluate from this.
All of the code that isn't directly related to this 1 and 0 output is already written, so you don't have to worry about any of that. It's just one section that you need to write, which will be clear when the challenge is released. If you go to the next slide, Theo. So submissions are open until 31. It's open now till the 31st of January. To register a team, teams can be 1, 2, or 3 people, but not more than 3. This is the register link. It's also will be shared through the Discord, Decoding Data Science Discord, and